Thank you, guys, and sorry to keep you waiting. Today the topic of today's session is machine learning poisoning. Since FIC is mostly about AI and how AI is going to change us, I thought that why not finish off this hacking lab with some conventional and non-conventional machine learning poisoning attacks. If you haven't, attended the past few sessions, this is me. I'm Shamir Ahmed, and here's a little bit of an introduction about me. Okay, threat model. There are two kinds of basically attack vectors when it comes to machine learning poisoning. Train time attacks is, one of them, where basically the attacker controls the training data itself. Now, the question that we want to ask ourselves is, does this usually happen? Yes, it does, because you are relying on a data set that is by nature a public data set, and that public data set contains, whether it's an image, if you're training a model based on image recognition, whether it's an image or whether it's a spam detector, or whether it's a federated learning data collector. It's basically, just a second. Now, what you see in front of you is a plane, and the testing example here is the recognition type is a plane, while if you are going to train a data set to recognize frogs, it means that that particular data set has to contain different kinds of images of frogs. And if you were to sort of distinguish between a frog and a plane, you would need to tell the data set to positively identify a frog in a set of different frogs. If an attacker was to poison, this particular image data set, here's how it would work. They would basically create an image that is unrecognizable, but still recognizable in some way that it is actually a frog. And what this does is this basically confuses the model in a way that the model does not actually know the model does not actually know the difference between a frog and a plane, because it is a poisoned image, and a poisoned image can basically, in a single point in time, poison the entire training data itself. Now, what you see in front of you right now is basically what's called a collision attack. And as you can see, there's a fine line of decisions between a base and a target. Now, this fine line helps the model to basically distinguish whether it's a plane or a frog. What happens is, when you create a deviation in this particular equation here, what basically happens is that the decision boundary actually gets dislocated in a way that the model's ability to basically make decision on that particular data set is a flawed way. Now let's talk about how poisoning actually works. You have one original image, and which is a clean base, and then you have multiple other variations of that particular image, which means that you have to have different images of that same image, but with a little bit of difference, so that it is recognizable by the model. Now, if the target instance is from a fish class, now what you see in front of you here is a very flawed way of training a model, because even some of these fishes cannot be recognized as fishes. So what happens is that if you were to poison this particular data set, what you would do is you would poison one image by inserting a fish into the data set of the dog, and once you poison that image, the output recognition Sorry. Yeah, so the output recognition of that, the recognition power of that particular model actually declines when you poison that image. Now, let's reverse the example by saying that if we were to identify dogs from fishes, and we would need a clean base and we would need a target data set. Now, what you see from a dog class perspective above is basically the flawed data that you feed into the model, and what you see at the bottom is basically the fish data. Now, the fourth image in the training data model is basically, we don't know if it's a fish or a snake. In real world scenarios, what happens is that when we have enormous amounts of data, and that data is public and in control of the attackers, it is fairly easy to poison that data based on a data set that is in a closed surface. So if you were to take an image recognition or a spam detection algorithm, those are based on public data. But if you were to train an AI model based on behavioral pairing, that is controlled data, which is inside your environment. So it is less harmful than this. So in a black box attack specifically, the base image is so close to the base data input is so close to the target data input that it basically confuses the function itself. And this particular attack specifically is for large-scale industrial data set attacks, and this works in a way that it is extremely harmful in a case that it not only affects the target and the base data set, but it also affects the time of that data set training as well. If the base image is present so near for the target image that there is no way to distinguish if that base image is the target image or not, then this is called a black box attack. And then the decision boundary in this case reverts to a way that the decision boundary itself is so curved and so flawed that the scenario is irreplicable. Now there's something called a poison polytope attack. So in a large-scale industrial data set, there are multiple attack vectors. There's the monotope attack is basically something that is related to inserting a single image or a single data endpoint, but a poison polytope attack is inserting multiple images or multiple poison endpoints, and this is what normally happens. If the data set is private, the monotope attack would be more feasible and it would work. If the data set is public, the polytope attack would be more feasible, and that would basically work more. Now, in this particular scenario, what you see in front of you, the target is called the fish, and the target here is fish, and then there's a clean data set and a poison data set. You would see that these clean label poisoning attacks basically work on small little variations in the data set itself. The clean and poison data set is virtually indistinguishable from each other, but at the same time, it is very, very realistic in a poison polytope attack. Let's try to push the poisoning further then. What is the next step? We have end-to-end training. We have any base images that would be involved. We have any attacker objective that would be involved. And then there are industrial systems. Meta poisoning is something that consists of basically inserting the poison into the data set and combining the training algorithm to train on the poison rather than the data set itself. So if meta poisoning works in a way that even if the data set poisoning attack does not work as intended, the meta poisoning attack works in a way that the size and the magnitude of the poison is greater than the size and the magnitude of the data set itself. For instance, if the data set is basically a function of a frog, and the parameters being passed through are the functions of a frog, then the poisoned entities would be frogs, but they would be so diversified and so changed in a sense in a larger magnitude that then that would be called data set poisoning. As you can see here, this is again a classic example of clean images and poisoned images. What you see here in front of you is clean images and poison images, clean images and poison images. Now if you observe closely, you would understand that the poisoned images corresponding to those clean images are slightly changed. Data set poisoning or on large industrial scales work on slightly changed data, and these are duplicative. So if you have a picture of myself and then you put a blurred picture of myself in 100 different ways, you would be able to effectively and efficiently poison that data set. This is basically the effectiveness and the attack success rate of a data set poisoning attack, and this is basically how it works. If you draw a graph between the success rate and the poison budget percentage, this is what you get from various kind of attack. This is a real world case study, by the way. These are different kinds of networks. We have convoluted networks, we have REST networks, and we have VGG13s. And these are basically the success rates of those networks related to the victim network itself. But then the question comes down to, could this actually work in a real world case, in a real world case scenario? Could machine learning poisoning actually work? Well, Google's AutoML, it's recently succeeded with 0.2% poison data, and this is the largest number of poison data success rate that we have found over the past few years. So yes, it does work. Data set poisoning is a real thing. It is a real-world attack vector, and we should be very scared of it, because we're talking about AI, we're talking about generative AI, and the data sets that we are using are mostly very, very public. We either import them from huggingface.co, or we either import them from any other generative AI website. But at the same time, the poison data success rate is enormous. Similarly, there are benchmarking processes to basically prevent this. We have feature collisions, we have feature collision ensemble, we have convex polytope, we have convex polytope ensemble, clean label, and hidden trigger backdoor. You can dive into these more when you when you study machine learning poisoning, but these are basically benchmarking processes of attacks versus the percentage of these, black, white, or red labeled. All right, guys. If you have any questions, feel free to ask them. I really apologize for keeping you guys waiting, and thank you so much for your time today.
Thank you. Thank you very much. Thank you very much, Amir. We're now jumping to the questions and answer session. If you want to ask a question, just raise your arm and we will bring you a microphone. Si vous avez une question, n'hésitez pas à lever la main Et nous vous apportons un micro. It seems we don't have any question. Thank you very much, Amir.
No problem. Thank you guys. Thank you for your time today. I hope to see you all next year.